In this video, we're going to look at intermolecular forces and how their strength is going to affect certain physical properties, like melting point, like boiling point, solubility, things like that. Keep in mind that the stronger the intermolecular forces, and I'll say IMFs for short, the higher the melting point and the higher the boiling point. So remember that solids have the strongest forces of attraction between molecules. To change from a solid to liquid, I have to break up those intermolecular forces. To change from liquid to a gas, I have to essentially break up almost all intermolecular forces. So if these forces are stronger, it's going to take a lot more energy to pull these particles apart from solid to liquid to gas phase. And therefore the melting points will be higher, the boiling points will be higher. Also, the stronger the IMFs, the lower the vapor pressure. And vapor pressure is just the pressure exerted by vapor that's above a liquid in a closed container. So if I have really strong IMFs in a sample, like in this first sample, not a lot of particles are going to be escaping into the gas phase because they need more energy to break those IMFs and escape to gas phase. Whereas if I have weaker IMFs, more particles have enough energy to escape the forces of attraction and escape into the gas phase. So if you have more IMFs, you have more forces holding the molecules in liquid phase and thus lower vapor pressure above that liquid. Less of it is escaping to gas. Also, the higher the viscosity, meaning it's going to be like a thicker, typically a thicker liquid if it is a liquid. Okay, so how do you know what IMFs are strongest? So typically when we're comparing particles with similar numbers of electrons, so taking out number of electrons as a factor, London dispersion forces will typically be the weakest. Dipole-dipole will be stronger than that, which makes sense because a dipole has actual partial charges in it. London dispersion is just when electrons end up on the same side, which induces a dipole. Hydrogen bonding is a stronger type of dipole-dipole, so it makes sense that would be stronger. And then ion dipole even stronger than that, which would make sense. Ion actually has a full charge and not a partial charge. So you should know this relative order: LDF, then dipole-dipole, H bonding, ion dipole. As you add electrons, remember that your London dispersion forces can become much stronger. If you add more electrons, the electrons are further from the nucleus, so they're more easily able to move to one side of the atom. So we say it's more polarizable. And also, if you have more electrons, it would induce a stronger negative partial charge. And on the other side, a partial positive charge. So if you're comparing things and they have the same types of IMFs present, so they are both London dispersion, or they're both London dispersion and dipole-dipole, so it's a polar molecule. Remember, all molecules experience London dispersion. Then the more electrons you have, the more polarizable it becomes. Remember, that's a really great word that AP loves. And the stronger the total IMFs, because London dispersion forces would become the most predominant factor. Okay, why is this? So the total IMFs is really additive. Dipole-dipole and London dispersion forces have an additive effect. Remember, all molecules have London dispersion forces, but only polar molecules have an additional contribution from dipole-dipole. So there's this equation which you don't have to know in any kind of way, but I just want to use this as an explanation. So the total attractive forces, notice, is a sum of two terms. There's this dipole-dipole term and an LDF term. So for instance, let's compare two different molecules. Let's compare molecules with similar numbers of electrons, so they would be essentially equally polarizable. So let's look at N2 versus CO. Okay, if I look at N2, it's a nonpolar molecule. Two N's are triple bonded together. Okay, so there is no dipole-dipole term, but there is a London dispersion factor term, and London dispersion force term, and there would be 14 total electrons, two N's, each 7 electrons, bringing in 14 electrons that would be contributing to this term. Okay, if I look at CO, okay, it's a polar molecule, and it would have a dipole-dipole term, and it would also have a London dispersion force term, which it also has 14 electrons, 6 plus 6 from oxygen, 4 from carbon. It would also have 6 from carbon, 8 from oxygen, sorry. They would also have 14 electrons going in. So notice if I'm adding these two terms up, CO would cumulatively have stronger intermolecular forces, because not only do they have similar London dispersion forces, but I have dipole-dipole forces on top of it. So for molecules with similar numbers of electrons, those that are polar and experience dipole-dipole forces would have stronger IMFs. Okay. If you're comparing things with the same type of force, so let's say I'm comparing CH3Cl versus C6H13Cl. So if I look at CH3Cl, it is a polar molecule. It's tetrahedral, but there are different atoms around it, so it's polar. So it would have a dipole-dipole term, and it would have a London dispersion factor term, and there's about 26 electrons if I add up all the electrons in here, not just valence electrons, but all electrons. There'd be 26 electrons in there. If I look at this other one, also polar, okay, has a Cl on one side, C's and H's on the other, so it has a dipole-dipole term. Also has a London dispersion factor term, but now I have 66 electrons going in on this. So which one would cumulatively have the most or strongest intermolecular forces? Well, it would be C6H13Cl, because they would both have dipole-dipole, but this one would have a larger LDF term. So the takeaway, again, you don't have to know that equation. I just wanted you to see that from a mathematical standpoint. For most problems, figure out the IMFs of all the compounds present. If you have different forces, go by whichever has the strongest predominant force. So hydrogen bonding would be stronger than dipole-dipole, which would be stronger than LDFs. If you're comparing things with all the same forces, then go by what's most polarizable, whichever has most electrons, or you can also just calculate which has the greatest molar mass. I wouldn't use molar mass as an explanation, but whichever has the greatest molar mass is going to have the greatest number of electrons, and be able to explain why. Anything that goes against this, they would give you evidence, and you just have to make sure that your claim makes sense based on the evidence. So if you have something that has different forces, but the thing that has the most electrons is the one that has the highest boiling point, then you would just say, oh, it must be because the London dispersion forces are greater due to the greater number of electrons. It's more polarizable. So you just want to make sure that your statement makes sense based on evidence. But for most problems, if you have different forces, go by what's the strongest forces. If you have the same forces, go by what has most electrons, and use that word, which is most polarizable. So take a moment, try this example, and then check your work. Okay, so for this example, it says complete the skeleton structure if needed. Just remember, drawings that they give you or structures they give you might not represent the actual geometries. So for this one, this O actually has two lone pairs, which would make this bent, and this would be polar. The way that they drew it here looks, on inspection, looks non-polar if you weren't figuring out geometries. So complete lone pairs if you need to. Always don't rely on how the image looks. Look at the geometry, the molecular geometries here. So this would be bent, and that would be a polar molecule. This would have lone pairs here. This is obviously polar, and this is nonpolar. Remember, anytime you have C's and H's only, it's going to be a nonpolar molecule no matter what the structure looks like. So I'm going to start by figuring out the types of IMFs. Okay, so this first one, the predominant would be dipole-dipole, would also have LDFs. Okay, the predominant would be hydrogen bonding. It also has dipole-dipole and LDFs. And this is nonpolar, so it would only have LDFs. So these all have different forces, so I'm going to rank them by which has the strongest predominant type. So ethanol has the strongest, so it would have the highest highest boiling point. And then this one would be slightly lower than that, and propane would be even lower than that. So propane's the lowest, then dimethyl ether, ethanol being the highest. Okay, take a moment, try this next one, and then check your work. Notice that these all have C's and H's, so these are all non-polar. Okay, so all of these only experience LDFs, London dispersion forces. So I'm just going to go by what's most polarizable. And if you're using an explanation on a free response, you make sure you use that word. So propane has the most electrons, so it is most polarizable. So it would have the strongest forces and therefore the highest boiling point. Methane would have the lowest. So we go methane, then ethane, then propane in terms of boiling point. Take a moment, try this example, then check your work. Okay, if I'm drawing the Lewis structure, that might help you figure out if it's polar or nonpolar, and you might not have to do that, but just showing you, here's H2O, it's bent, so it's polar. Here's H2S, it's bent, so it's polar. Na2S, be careful, that's an ionic compound. I'm not going to show a Lewis structure with lines because those would be covalent bonds. So right away, ionic compounds would always have higher melting points than anything that's molecular. You're not breaking intermolecular forces, you're actually pulling apart intramolecular forces. Ionic bonds, if you're melting an ionic substance, you're pulling apart that lattice, which is essentially made up of all ionic bonds. H2O, you're breaking up H bonds, also dipole, dipole, and LDF. H2S, you're breaking up dipole, dipole would be the strongest, also LDF. And this is ionic. They are all different types, so I'm going to go by the different types. So Na2S would be way, way high. H2O would be much lower than that. H2S even lower than that. So don't forget, if you're comparing an ionic compound, that is going to have a much higher melting and boiling point than anything molecular. Take a moment, try this example, then check your work. So always figure out the types of IMFs present. So HF would have hydrogen bonding. It would also have dipole-dipole and LDF. HCl has its H not bonded to NO or F, but it is polar, so it would only have dipole-dipole, also LDF. And same with HBr. It's polar, but doesn't have H bonded to NO or F, so it would be dipole-dipole and LDF. So first, go by forces. I would say that HF would be the strongest IMFs because it also includes the H bonding. Then between these two, which have the same types, go by what's most polarizable for having the strongest forces. So HBr is more polarizable, has more electrons, so its boiling point would be higher than HCl. So HCl would be the lowest, then HBr, and then HF. So notice, always start by finding the types of IMFs, and even before that, it might help you to just figure out, is it polar or nonpolar? And then you're just comparing the strengths. If they're different, go by which is the strongest of those. If they're the same forces, go by what's most polarizable and has the most electrons. And instead of looking at electrons, if you want to calculate molar mass and go by whichever has the highest molar mass, that's fine. Just don't use molar mass as your explanation. Use most polarizable. Take a moment, try this example, then check your work. Okay, for this example, if this is like a carboxyl group, this has a C double bonded to an O and an OH, that's making it polar. It also has hydrogen bonding in there because you have the H bonded to the O in there. So both of these have H bonding, hydrogen bonding, dipole-dipole, and London dispersion forces. So I'm going to go by, since they have the same types, go by what's most polarizable for having the strongest intermolecular forces. So it would be this second one here. This would be having a higher boiling point than this first one. And this actually just has a much longer hydrocarbon chain than this one. Okay. Take a moment, try this example, then check your work. Fully explain why the melting and boiling points of the halogens increase down the group. So all the halogens are diatomic, they are nonpolar molecules, so we're looking at the same type of intermolecular force, so we're looking at London dispersion forces, which is most polarizable. Okay, so all halogens experience LDFs, but larger molecules are, I don't know why the A got cut off, are more polarizable and have stronger London dispersion forces. So I2 is most polarizable, and F2 is least polarizable, so it would have the weakest LDFs. Take a moment, try this example, then check your work. Notice what types of compounds these are. I am comparing all ionic compounds. So if I'm melting them, I'm breaking ionic bonds in all of them. Well, how do I judge the strength of an ionic bond? Remember from last chapter, that is the Coulombic force of attraction. So whichever has the greatest Coulombic force of attraction is going to have the strongest ionic bonds and have the highest melting point. Well, how do I know which ions attract each other more? I'm looking for the greatest charge and the smallest radius. And again, this is that Coulomb's law, which you don't have to memorize, but you do need to know you're looking for the greatest charges and the smallest radii. So this is plus 1 minus 1 plus 1 minus 1, but this is plus 2 minus 1 plus 2 minus 1. So I'm looking between these two, which have the greatest charges, but then mg is smaller than Ca. Remember, atomic radius is largest bottom left-hand corner of the periodic table. Make sure you know the trend. Make sure you could explain that trend because shells are increasing, going down the group, and going across the group you have a greater effective nuclear charge. That's why radius decreases that way. Take a moment and look at these. So first, just defining viscosity. Viscosity is the resistance to flow. You can also think of it as like the thickness of a substance. So something like honey is more viscous, has a higher viscosity than water. It's harder to pour, it's harder to flow, it's a thicker substance. So we had said that if you have stronger intermolecular forces, that's going to cause it to have a higher viscosity. So if you look at this example, take a moment and figure out which of the following would have the greatest viscosity. So I would say these all are hydrocarbons. Remember, if you have C's and H's only, it's automatically a nonpolar molecule no matter what it looks like, so you don't have to think about drawing it. So these are all nonpolar, would all only experience LDFs. So which one would have the strongest intermolecular forces? The most polarizable would be decane. Okay, has the most polarizable, so it would have the strongest LDFs. Vapor pressure you might be asked about. Just in a little background about vapor pressure in case you haven't taken a chemistry class before. At any temperature, some of the molecules on the surface of a liquid have enough energy to escape into the gas phase. So remember that if you remember the Maxwell-Boltzmann distribution curve, not every single particle has the exact same kinetic energy. There's really a wide range of kinetic energies, and on average, the sample has an average kinetic energy. But in any sample, some particles are moving much faster and have enough energy to escape the attraction of the liquid and move into the vapor phase. And as the number of molecules in the gas phase increases, some of the gas phase molecules also can turn back into liquid. They can strike the surface of the liquid and turn back into liquid. So you get, if you have a closed container, you get this equilibrium condition where some of the particles are evaporating and some of the particles are condensing, and that's happening at the exact same rate. And vapor pressure is just the pressure that's exerted by the gas in a closed container above the liquid once they reach this equilibrium condition. Anything that has a high vapor pressure is said to be volatile, and it can evaporate easily. And a lot of them come with like a hazard warning that something like butane, something like even gasoline or alcohols, some of them can, if a lot of it's evaporating, it can cause a fire hazard or a flammability hazard, I should say, where, it could cause an ignition if there's a flame nearby. So if you're asked about vapor pressure, just remember that this is going to have like an inverse relationship with the strength of IMFs. So usually when I say, okay, what has the highest boiling point, highest melting point, highest viscosity, you're looking for the highest or strongest IMFs. If you're looking for the highest vapor pressure, you're looking for the weakest IMFs, because that means that your sample is not going to be held together by strong forces of attraction and more particles can escape into the vapor phase. So take a moment, try this example. Okay, so this is LDFs only. It's nonpolar. This is nonpolar LDFs only. This has an OH group, so it can do hydrogen bonding, so also dipole-dipole and LDF as well. So if I'm looking at this, butanol would have the lowest vapor pressure because it has the strongest forces of attraction. Okay, then between these two at the same forces, butane's more polarizable, so it would have stronger forces, so butane would be next, and ethane would actually have the highest vapor pressure because it has the least forces of attraction between the particles. So remember, vapor pressure will be higher for liquids with weaker IMFs because the substance can more easily overcome these IMFs and break away into the vapor phase, increasing the number of molecules that are in the vapor phase at that temperature, and thus increasing the pressure above the liquid. Okay, when it comes to solubility, substances with similar IMFs tend to be miscible or soluble in one another. This is an observation, but we need to be able to explain the why. So in order for a substance to dissolve, two different things have to happen. They have to overcome solute-solute IMFs. Okay, so the attractions between the solute have to break up. The attractions between the solvents have to break up. And then you have to form attractions between the solute and the solvent. Okay, so what you want to do is whenever you come across a solubility question, you always want to mention the types of IMFs you're overcoming or breaking up, and you also want to mention the types of IMFs that would be formed between solute and solvent. So basically, you need to make sure that the solute and solvent attract each other just as much, if not more, than the solute and solute and solvent and solvent. Never use like dissolves like on the AP exam. Make sure you're explaining in terms of IMFs, and make sure you mention both substances in your answer. So let's look at an example. Would nonpolar molecules dissolve in polar solvents? So let's look at something like hexane, C6H12, and H2O. Let's talk about the IMFs we need to break between the solute particles. So C6H12 with another C6H12. What IMFs would I have to break up? I'd have to break up LDFs because they're nonpolar. What would I have to break up between the H2O molecules? They attract each other through hydrogen bonding. What IMFs would form between the solute and the solvent? Only LDFs, because C6H12 is nonpolar, and the only thing it's capable of doing is forming an LDF as its intermolecular force of attraction. So would this dissolve? No. Essentially, the water is going to form much stronger IMFs with another water molecule than it would with a hexane. So the water is going to stay attracted essentially to itself, and that hexane is not going to be able to mix in. The solvent-solvent interactions, H bonds that have to be broken, are much stronger than any solute-solvent interactions, LDFs, that would form. So water would end up being more attracted to itself. And when I say itself, I mean another water molecule. And that's why you're going to get, if you put something polar and nonpolar together, you're going to get these two distinct phases where the solute will remain with the solute and the solvent remains with the solvent. Okay, let's talk about nonpolar with nonpolar. So instead, if I put that hexane in CCl4, okay, we already said we would be breaking up LDFs in the hexane. We would be breaking up LDFs in the solvent, and what would form between them? Also LDFs. So that's why, yes, nonpolar would dissolve in something nonpolar. The solute and solvent can attract each other just as easily as they would attract their same molecules, and they would be able to mix together. LDFs would be broken, but LDFs would be formed, and they would be comparable. Would polar dissolve in polar? So something like NH3 and H2O. So the ammonia particles, I'd have to break up H bonds between them. I'd have to break up H bonds between the solvent particles, but then H bonds would form between the ammonia and the water. So typically polar solutes will dissolve in a polar solvent because, again, they contract each other. They have just as much attraction for each other as they do for their same type of molecules, so they would be able to mix together. So in your answer, be sure to mention IMFs that would form between the solute and the solvent. Take a moment, try these examples, and then check your work. So ethanol, would that dissolve in water? Yes. Okay, I'd have to hydrogen bonding could form between them, just so they would attract each other just as much as they would attract their same particles. Hydrogen bonding would be broken, but hydrogen bonding would also be formed. Octane, would that dissolve in bromine? Bromine's Br2. Remember, it's diatomic, so nonpolar. Yep. LDFs everywhere, right? They both exhibit LDFs, but they could also exhibit LDFs when mixed together. So make sure you're not only mentioning the types of IMFs within the sample of a pure solute or solvent, but mentioning what would form between solute and solvent. Propane and water, no, the water would end up being actually more attracted to itself in the sense that water molecules would form H bonds with each other, which is stronger than any type of intermolecular force that could form between the propane and the water, which would only be LDFs. So again, notice my explanations mentioning the types of IMFs and mentioning both substances. Question, why are some ionic compounds insoluble in water? What would make something insoluble? Well, that would mean that it would have to be more attracted to itself, essentially. So some ions are going to be more attracted to each other than they would be to the water. So essentially, the ionic bonds that must be broken are much stronger than the ion dipole interactions that would be formed. And this does happen in some compounds. A lot of fluorides are insoluble because fluorine is such a small, or fluoride ion is such a small ion, and it has a really high electronegativity as well. Take a moment, try this example, and then check your work. Which is more likely to dissolve in methanol, alkane C10H22 or liquid HCl? Okay, well, remember, alkane, anything with C's and H's, is nonpolar, and this is a polar molecule with dipole-dipole. Make sure you explain your answer in terms of each solute and hexane. So HCl would form dipole-dipole attractions with methanol. Okay, it can't form hydrogen bonding. There is no H available here for hydrogen bonding. It's bonded to an NO or F. And the alkane would only form LDFs with methanol because it's nonpolar. That's all it's capable of forming. So the HCl, since it could form stronger attractions with that solvent, it's going to be more soluble.